Hi you, and continue with the schedule of the MCA. It's my great honor to introduce our distinguished winner prize speaker, Professor Deng. Currently a professor at the University of Chicago, he earned his PhD from Princeton University in 2015 after completing his undergraduate studies at the Massachusetts Institute of Technology and Peking University. He has also had positions at the University of Southern California and the Curran Institute of Mathematical Sciences. Professor Deng's work has had a profound impact on the theory of partial differential equations, with renowned contributions and interests in nonlinear dispersive and wave equations, fluid dynamics, harmonic analysis, probabilistic theory of PDEs, and statistical physics. Apart from the MCA Prize, Professor Deng has been awarded last year at the ICBS Frontiers of Science Award in Mathematics. His honors also include a Sloan Research Fellowship in 2021. Today, we are privileged to hear his talk, Hilbert's sixth problem, Particles and Waves. Please let us give Professor Deng a warm welcome.
Thank you. This is, I'm very happy to be here to present my recent work. So this is a joint work with Zaher Hani and Xiao from University of Michigan. Okay, so since this title contains the Hilbert sixth problem, so let me start from a brief description of the scope of the problem that we'll be working on. Okay, so first, so this is a big title of the Hilbert sixth problem, which states the mathematical treatment of the axioms of physics. Of course, this is like an extremely broad topic, and if you interpret broadly, it may contain everything, essentially everything in modern mathematical physics. However, when Hilbert actually proposed this problem in his lecture in 1900, what he actually had in mind was actually some particular problems in kinetic theory, which was about maybe 30 years old at that time. So in particular, Hilbert wrote this article, complimenting his lecture in 1900, and there he kind of made more specific statements about the list of problems he proposed. And here, let's take this quote. He mentioned this problem of developing mathematically the limiting process, which lead from atomistic view to the laws of motion of continuum. Okay, so basically, on the one side, we have this motion of continuum, which basically you think of fluid equations. On the other side, we have on the microscopic level, we have the atomistic motions of atom-sized particles. Okay, so the question is kind of to bridge like these two scales and in a kind of a rigorous mathematical sense. So see, this is a kind of a really non-trivial thing. The reason is that if you think of the fluid equation, you're talking about the evolution of a vector field, where at each point in X, there is a velocity. However, if you really think of the subatomic particles, then these particles, the velocity of these particles is not like continuously distributed. It's not that two molecules that are close to each other that don't necessarily have close by, nearby velocities. So see, this is a highly non-trivial thing to kind of make a bridge between these two phenomena. And this problem, you see, since it was proposed in the 1900s, it has been studied kind of for the whole 20th century, and people now have much better understanding of this limiting process, which I'll describe in the next slide. Okay, so there is this point of view, the kinetic point of view, where you think of this process from microscopic of atoms to the macroscopic of fluids. So there is a two-step process. So you first go from the microscopic picture to the so-called mesoscopic picture, where you we'll describe in details later, but basically you are describing the motion, the statistical information of the whole system by the evolution of density function, and this density function is satisfying this so-called Boltzmann's kinetic equation. So basically you think, you know, there are so many, there are infinitely many, almost infinitely many particles, you know, in this room, for example, and then you're asking, so given a small region of positions x, given a small region of velocities, so how many particles, kind of what proportion of particles kind of belong to this small box of position and velocity? Okay, and this is described by this density function, which describes the statistical behavior of these huge systems of moving particles. Okay, and this function is going to be satisfying this Boltzmann equation, which is the main object of this talk. And then there is this second step, which is called hydrodynamic limit. Basically, the thing is that this density function, like described by the Boltzmann equation, like in the long time limit, is going to relax to some particular equilibrium state. And due to these entropy considerations, this equilibrium state will be a Gaussian function in the velocity variables. So basically at each point in x, so there is a kind of a Gaussian variable, and the Gaussian variable, of course, it has a mean, and this mean is expected to be the velocity that you see in a velocity field of this fluid. Okay, so this will be the second step of the hydrodynamic limit. Basically, the limit is, we'll see that basically it's kind of time going to infinity, or kind of the collision rate of particles going to infinity. And the first kinetic limit, of course, is really the degree of freedom, the number of particles going to infinity. Okay, so this is the kind of the two-step process that people have been understanding. Of course, there are other interpretations, but for now, let's focusing on this canonical kind of interpretation. So let me also mention that the second hydrodynamic limit has been well understood thanks to the works of many mathematicians throughout the century. For example, let me just list the work of Bardos, Ukai, Livermore, Gauss, and Raymond Gallagher, and many other people. Yeah, so there has been satisfactory results concerning the limit going from Boltzmann equation to either the compressible Euler or incompressible Navier-Stokes equations in different time regimes. So I'll not talk about too much about that part. So the main focus of this talk will be on the first limit, the kinetic limit, or we go from the interacting particle kind of atom systems to the Boltzmann equation. Okay, and of course later on we'll mention how do we really connect these two steps to finally complete this program of Hilbert, but that's in the second part of the talk. Okay, so this is the picture. We have n particles in the finite box. So you can consider periodic box or kind of whole space, but with smaller and smaller probabilities when you go to infinity, but it doesn't matter. So let's consider we have a box. And of course, this n is going to infinity in the kinetic limit. The number of interacting particles is going to infinity. Okay, and then there are these interactions. The interaction between particles, so there are different kind of interactions. For now, let's take the mathematically simplest interaction, which is the elastic collisions. Like when you have two particles, they collide when they directly kind of meet each other. And of course, there is the parameter epsilon of the size of particles, which is going to 0 in the limit. So think of large number of small particles that fits in this unit domain. Okay, so there is another relation between this number of particles and the size of particles and an epsilon. And here this one is called the Boltzmann grad scaling, which in the three-dimensional shows n times epsilon squared equals alpha. So basically this alpha is, can be understood as a collision rate. Basically think of any single particle, kind of the number of collisions with other particles is going to expect, kind of on average, is going to be this alpha. So when alpha is big, which means you have a higher density of particles and you have many collisions. When alpha is small, you're having kind of very few collisions, like on average. Okay. So this is the this Boltzmann scaling. In our talk, we'll be assuming alpha is either constant or kind of growing kind of very, very slowly. We'll see. But essentially, this is what we assume in the so-called Boltzmann scaling. I mean, there are other kind of scaling regimes, and which is completely different, kind of requires completely different mathematical treatment, and that is kind of there are still many open questions there. But for now, let's restrict ourselves to the Boltzmann graph. Okay, so this is the formula. So I'm just showing this page just to show you that this is a completely elementary formula describing the elastic collisions of hot spheres. So the first line tells you that if there is if the distance between the centers of the atoms is bigger than epsilon, then okay, there is no collision, everything goes linearly. And the next three lines tells you when there is a collision, then the formula gives you like this thing where omega is the vector basically connecting the center of the particles. So this is basically, I'll not say how it comes from, it just basically follows from the undergraduate physics using the conservation of momentum and energy. Well, the point is that it's a very simple kind of elementary formula. For these two-body collisions. Okay, so of course I'm saying this system is simple in the sense that if we have a finitely many particles n, this is a relatively simple system. But when n goes infinity, of course it becomes completely non-feasible to track the behavior of all this collection of huge number of particles. So of course we are going to take a different point of view because these particles are kind of identical. So we don't really care about exactly each individual particles how it goes. We really care about is the statistical kind of properties of this system. Basically, the basic quantity we are looking at is a density function telling us how many particles, what proportional particles belong to this small region, like which is given by this probability density function. So this is the statistical point of view. So see there is this so-called S particle density functions. Of course, you can take S equal 1, the probability of distribution of the Z is basically X and V. X is a position and V is a velocity. So this is the distribution of a single particle. And then you can ask, of course, a joint distribution of 2 particles, 3 particles, and in general kind of S particles. Okay, so this is the basic quantities we are looking at for this system, which we'll see will be described by this Boltzmann's kinetic equation. And then, of course, there is this initial data. Like initially, we're assuming that these different the states of different particles are kind of independent from each other. So this is a very important kind of base assumption, in going back to the original kinetic theory of Boltzmann, which is referred to as the molecular chaos. Okay, so this is something that allows us to write down this Boltzmann equation and to derive it kind of on a formal level. Okay, so this you have this complete factorization, and then let's say the initial density function, one particle density function is given by this F initial. And then the question, of course, is how to describe the time evolution of these density functions. Of course, whenever you have positive time due to collisions, the states will no longer be independent. But how to describe this limit, these densities in the limit n goes infinity? Okay. This is a setup of the problem. And then one kind of key feature of the theory is the so-called propagation of chaos, which basically tells you, I mean, it's a highly non-trivial thing, but we're kind of expecting it to happen, that even though for positive times, due to collisions, the states of the particles will no longer be independent. However, this independence is kind of restored kind of in the limit n goes to infinity, which means that these kind of correlations, non-independence, is going to vanish eventually in the limit, in the kinetic limit when n goes to infinity, even for positive time. Okay, so this is kind of a key thing, in the whole theory, both physically and of course mathematically, that will allow us to derive this evolution, which is given by the Boltzmann equation. So we'll get to that kind of in more detail in a later presentation, but this is the kind of the intuition that we are expecting. Okay, so let's say we assume this is true. Then there is this Boltzmann equation which describes the evolution of the one particle density. Intuitively, you are thinking of the left-hand side as it's a linear transport, which basically means that if there is no collision at all, so the particles do not interact, then everything goes linearly, then this density function is going to kind of go through a linear transport. And on the right-hand side, so there is this quadratic so-called collision term, which tells you like how the density changes due to collisions. Okay. So basically, right-hand side tells you, how many particles is going to get to this position x and velocity v due to collisions, and how many particles is going to move away from this position x and velocity v. And it's given by this integrals, which is given by the possibility of a collision between this particle and another particle that produces this velocity. Okay, so this has been done kind of in the 1860s, 70s, and then the question, of course, is how to actually justify it, in a completely mathematically rigorous manner. Okay, so maybe let me go through a little bit of history. So, the starting point was this Boltzmann work of Boltzmann, early Maxwell, in the 1860s, 70s. And then maybe the first kind of mathematical treatment was started by Grad and collaborators in the 1940s, 50s. Well, they first raised this first mathematical formulation of this question, this kinetic limit. And then they introduced this BBG hierarchy approach to this half-sphere system, which was originally developed for other purposes. And then we see this first major result in this direction of Lanford and also by King in 1975, where they provided the first rigorous derivation of Boltzmann equation, from the physical system we just described, for sufficiently small time t less than 1. Okay, so we'll see basically what happens here is that sufficient small time, if you think alpha is like 1, the collision rate is like 1, then basically in the small time, each particle is going to have on average like a very tiny amount of collisions, which means that each particle is going to have at most 1 collisions, and the number of particles that has collisions is tiny. Kind of, on average, there is a very few collisions in this region. So similarly, there is a work of Illner and Proverenti in the 80s where they obtained long-time results, but in the case where the collision rate is tiny. So again, this is a kind of perturbative regime where the average number of collisions experienced by a single particle is extremely small. Okay, so of course, later on there has been a lot of development. So starting from the work of Gallagher, St. Raymond, Texas in 2014, where they actually located and fixed a gap in the original proof of Lanford, and they also obtained kind of new contributions, including these more explicit convergence rates and the more kind of precise descriptions of the limit. And then there has been, in the last 10 years, basically has been a lot of activities in this direction. Centered around, first of all, various linear models worked by Bodino, Gallagher, St. Raymond, and Bodino, Gallagher, St. Raymond, Simonella, centered around these various linear models and also fluctuations around this nonlinear Boltzmann equation, which again kind of in the kind of linearized context. Okay, so this is just, so since we have different things to talk about and not just this one, so we can only give a kind of a very brief discussion of the history. And let me just close the first half of first part of this talk by this question of this long time problem. So you see, in the long time problem, like you're having this alpha, the collision rate being very large, or maybe the time being very large. So in the whole period, basically each of your particles is expected to have like a 100 or 5,000 collisions. So this is completely different from the short time perturbative regime where each particle is going to have like a very few number of collisions. Because of the convergence, this difference between the convergence and divergence of power series expansion. Okay, so this is the question that can we derive the Boltzmann equation from the high-speed system for arbitrarily long times as long as the solution to the Boltzmann equation exists. Okay, so this would be the first result that works in this kind of collision dynamics in the non-perturbative setting. Okay, so we'll see that there is a fundamental differences between the perturbative setting and non-perturbative setting, and this is kind of related to the main theorem that we'll introduce in this lecture. Okay, so maybe is there any questions for this part? Okay, so we can. Second part is the Hilbert-6 problem for waves. The first part we have Hilbert-6 problem in the classical setting for particles, and here we have the in the kind of quantum setting, concerning waves. So okay, so there is this. The development of quantum physics in 20th century, and then there is especially this duality between waves and particles. So this allows one to ask the same question. Like essentially, every question that has been asked, in the classical setting, can be asked in the quantum kind of in the setting of wave interactions, and this has led to the development of the theory of wave kinetic theory, or called wave turbulence. And here in the second half, we'll be talking about the same question corresponding to the Hilbert-6 problem, i.e. this development of the kinetic theory in the setting of wave interactions. Okay, so this the role of Boltzmann equation in this setting is replaced by that of the wave kinetic equations. So we'll see the wave kinetic equation in a few slides, and we'll see they are extremely similar to the classical Boltzmann equation. So this started with the work of various people kind of in 1920s, 30s concerning various different models. It's essentially models on the lattice and models essentially models on the lattice. And then here, if I only mention one person in the development of wave kinetic theory, it will be Zaher, who not only kind of developed this whole theory into into a systematic theory of treatment of wave system, but also he especially discovered this so-called KZ spectrum, which makes a close link to the theory of turbulence, and this is part of the reason that nowadays we're having this name of wave turbulence. Okay, and of course, also there is work of Boltzmann, which was concerning this wave kinetic theory for water wave, and it's particularly important because it has been used actually in applications to do actual forecasts of the ocean surfaces, which is on the picture on the left hand side, where we actually solve these wave kinetic equations to make these predictions about the evolution of ocean surfaces because of all these kind of randomness. And also the right hand side is a picture on plasma. Again, there is a lot of wave turbulence involved in the study of plasma. Okay. So let me describe a little bit the setup. You see this is a pretty in close analogy with the particle setting. So first of all, instead of particles, we are having these waves, and in general, in the so-called homogeneous setting, these waves are represented by Fermi modes. So they have kind of a single frequency and a single group velocity. But in terms of these Fermi modes, they are kind of homogeneous in space, which means they have same intensity everywhere in the space variables. There is also this inhomogeneous setting where you have these instead of Fermi mode, you have these wave packets where you have these wave packets are not only localized in the frequency variable, they are localized in the space variable x, and at different point of x, you have different wave packets, which means you may have different intensities and so on. Okay, so we have these waves representing replacing particles, and then there is a domain of size L. So this L is going to infinity. So basically, the way you think of it is that you have a big box of size L, and then think of Fourier modes. The Fourier modes by duality will be a kind of lattice which matching size 1 over L, and this 1 over L goes to 0. So basically, if you think L goes to infinity, then the mesh size of the lattice will go into 0, and then the number of, the degree of freedom, the number of different Fourier modes will go to infinity as this L to the 3, like in 3 dimensions. Okay, so this is a number of interacting objects we have in this wave system. Okay, so we have objects, now we have interaction between objects, and here we have these collisions between particles, which are replaced by the nonlinear interactions between these waves, and there is a parameter alpha which represents the strength of the nonlinear interaction, which will go to 0 in the limit. We'll see in the next slide. And then these nonlinear interactions, in general, it can be kind of represented by any kind of nonlinear dispersive equations. So in this talk, we're focusing on a kind of canonical case, which is a cubic Schrodinger equation. In some sense, it is a canonical nonlinear dispersive equation by a kind of, if you consider suitable kind of a long wave limiting regime. But okay, so this is a cubic nonlinear Schrodinger equation. So we have this parameter alpha on the right-hand side, which represents the strength of the interaction, which is going to 0. Okay, so let's review a little bit the picture here. So we have a large box, from 0 to L, and this L is going to infinity, represents the number of interacting waves. And then we have parameter alpha, which goes to 0, which represents the strength of interactions. And then in the homogeneous case, there is actually some flexibility between the scaling relation between these two parameters. And we assume this alpha equals L to minus gamma for some kind of scaling parameter gamma between 0 and 1. And by the way, in the inhomogeneous case, so this gamma is essentially kind of fixed to be 1/2, which corresponds to the Boltzmann-Grad scaling law in the particle case. But here we have kind of a little bit more freedom concerning the scaling laws. Okay, so we have these waves. We have this interaction by the cubic Schrodinger equation. We have these kinetic limits. And then we are looking at the statistical quantities, okay, as we did in the particle case. So there is one kind of difference, is that the U, which is a wave function, the U itself is not probability density. Basically, the mod U square is probability density. Okay, so this will lead to some slight differences between the description of the statistical quantities. For now, let's say we set up the initial data of this nonlinear Schrodinger equation. So basically, you see this is a random Fourier series with the Fourier modes being independent Gaussian variable. So here, if you look at the first line, the eta k is IID Gaussian random variables. Okay, and which means that different Fourier modes are independent. So this exactly corresponds to this molecular chaos. Different objects, the states of different objects are independent. Okay, and then there is this profile square root of an initial, which is essentially will be the initial data of the system. Okay, and then we set up this so-called initial chaos assumption that initially the Fourier modes, the different Fourier modes are independent of each other. And let me mention this point that the role of one particle densities and the role of general S particle densities in the Boltzmann case will be replaced by the role of 2-point correlations and the role of 2 S-point correlations. As I said, it's only the square, norm square of the wave function that represents the probability density. Okay, so there is a kinetic time which is equal to this alpha minus 2. This kinetic time is calculated again like in the same spirit as the Boltzmann-Grad scaling. It's a time where where each wave is going to interact with 2 other waves. It's going to have its first nonlinear interaction. And then we expect this propagation chaos, which will be the same as the particle setting. That independent Fourier modes the independence should be restored in the kinetic limit. In other words, if you fix any rescale time tau, remember we have this kinetic time here, then the different, the different firm modes at different frequencies, kj, will be asymptotically independent, again, in the kinetic limit where L goes to infinity. Okay, so this is the physical picture, and of course, as I said, we're looking at this second moment, the two-point correlation, which plays the same role as a one-particle density, and this is going to satisfy this wave equation. So you see that this delta function. So if you go back to the page of Boltzmann, you see that this is exactly the same delta function in 3 dimensions. And then the only difference between Boltzmann and wave kinetic is that you're going to have a quadratic term on the right-hand side for Boltzmann because you're having quadratic collisions. But in the wave kinetic setting, you're having a cubic equation on the right-hand side because you're having this, you're starting with a cubic nonlinear Schrodinger equation. But otherwise, it's the same integral on the same kind of submanifold you're integrating, and you have this, except you have this different nonlinearity. Sorry. Okay, so a few remarks. So first one is you have inhomogeneous setting, where you have this transport term. And second thing is that the whole collision integral is extremely similar to that of Boltzmann. So in some sense, this hard sphere collision system is in exact correspondence to this cubic Schrodinger equation, like with this particle wave kind of correspondence. And finally, there is something called the quantum Boltzmann equation, which I'll not talk about, but it turns out to be the precise linear combination of the Boltzmann equation and the wave kinetic equation, and the derivation of that quantum Boltzmann equation is still open, completely open at this time. Okay, so maybe let's go to the kind of the previous mathematical results. So this, you see, this progress is much kind of slower than the progress in the Boltzmann setting in the 20th century. So the first works, as I listed here, Schwang in the 70s, Xiao in the 2000s, Semhofer and Xiao in 2008, they were all concerning the linear problem. Linear problem means that you have a linear Schrodinger equation with random potential instead of a nonlinear Schrodinger equation. And this has been, there has been a lot of progress, and in the most recent work, Semhofer and Xiao has been extending it to even kind of time going to infinity, which exhibits this so-called quantum diffusion phenomena. So there are still open problems there, but okay, so this is much better understood. So then the first kind of nonlinear problem, real nonlinear problem, which was discussed by Lucas and Schwang in 2011, where they consider this nonlinear Schrodinger equation, but at equilibrium. And but since that, there has been a lot of activities. So the next work was due to Buckmaster, Germain, Hani, and Chata. Again, they consider starting with nonlinear and off equilibrium. They were able to get to a time scale which is much less than the kinetic time. And then the subsequent work by myself and independently by Kohler and Germain were able to get to the kinetic time to the power 1 minus epsilon, so very, very close to kinetic time. And then the first result we get to the kinetic time, again, I mean a small absolute constant multiple of the kinetic time, was by myself and Hani in the serial papers in 2021 to 2023. Also, there is at the same time there is work of Stephanie and Chuan that dealt with the system with noise, and they reached the same kind of result conclusion of sufficiently small constant times kinetic time. Okay, so in this page we have matched basically the state of art, for the Boltzmann problem, which is valid for sufficiently small time, where you start to have very few interaction, very few collisions, then you can derive this whole result of kinetic theory. Again, the question is what happens for much longer times, and now I think this is the correct time to introduce our main result. We have the first main result with joint works with Hani in 2023 where we first derive this long-time result, this long-time kinetic limit in the setting of the wave King equation from the Curie nonlinear Schrodinger equation. So in the wave setting. So this is the theorem. This is how it reads. Suppose a solution to the wave equation exists on any given time interval. This tau star doesn't have to be small. The solution doesn't have to be small. So everything can be arbitrarily large. Then we have these approximations. So you see these 2-point correlations is equal to the solution to the wave King equation plus the explicit error term that goes to 0 in the kinetic limit. And this, of course, is true on the whole kind of whole time interval as long as the solution exists. So this size is this space is limited, so I could not spell out the full statement of theorem. So full statement of theorem would also include this propagation of chaos, the multi-point correlations being the tensor product of the 2-point correlations, and 2-point correlations given by this explicit approximation formula. Okay, so this was the result of a few years of study since 2018 to 2023. We have been focusing on this wave turbulence problem. And then after this, we realized that the same techniques we use in this theorem 1 can also be applied to the problem of these colliding particles in connection with the Boltzmann equation. So we started studying that problem. And then the next theorem we proved in 2024, we joined with Hani and Xiao, we are able to derive the same result, long time kinetic limit, in the setting of the hard sphere particle, in the setting of the hard sphere system. Again, here we have the Boltzmann equation. Suppose the solution exists on the, again, arbitrarily large given time interval. Then we not only have the 1 particle density, we have the s particle density. So the first half is the propagation of chaos. The s particle density is a tensor product of 1 particle densities, and then plus the error term which goes to 0 again as an explicit rate. And then of course the 1 particle density is going to be the solution to the Boltzmann equation, of course in the kinetic limit. Okay, so this is the second part where we derive this Boltzmann equation from the sphere system, and with this, since this allows to arbitrary long time, I didn't say, but it also allows for arbitrarily large kind of collision rate. So then this allows us to connect this first kinetic limit to the second hydrodynamic limit. So basically what happens in the hydrodynamic limit is that this collision rate is going to infinity. Or equivalently, by rescaling, you can think of this time t star is going to infinity. So since we have this result with arbitrary large t star, we can connect it with the hydrodynamic limit and finally, complete this Hilbert's original program of going from the particle atom systems to the Boltzmann kinetic equation and then to the fluid equation. So this is the third theorem, again with joint work with Hani and Ma in 2025. So this is just one example. So basically, you start with the density function given by the so-called Maxwellian. Okay, this Gaussian distribution in V. Then in the limit, you are going to see this. You're going to preserve kind of this Maxwellian form, and then these parameters, this rho and this u and this t, they are going to evolve exactly according to the compressor Euler equation. Well, u is a velocity field, rho is a density, and t is a temperature. So again, I didn't write down this here, but there is if you go to even longer time scales where you really see this dissipation effect, then you are going to, if you perturb around the global Maxwellian, you are going to see the Navier-Stokes equation as on the next level, in the incompressible Navier-Stokes equation. Okay, so this is the thing. Maybe a few remarks. So here as I said, it is allowed that these long times to actually go to infinity, well, except that the rate has to be relatively slow. It's a kind of a double log thing. It's a very interesting question whether this double log can be improved, but this is kind of what we have for now. So at least we can allow them to go to infinity with a little bit of rate. And the second thing is that we are doing Navier-Stokes, as I said. Like Navier-Stokes basically requires like that you go to even longer time where you see the dissipations, caused by the viscosities of the collisions. Okay, so maybe if you have a few more minutes, let me describe a little bit of proof. So all these papers add together is like 400 something pages. So I wanted to summarize them in 3 slides. So it has to be kind of very concise. So let me just mention a few important points in the proof. So the first point is the time layering. So the reason is that, okay, remember we know the short time result. So if you have from 0 to much before the very first collision, we know how to describe these dynamics. Okay, but now we have 100 collisions. Okay, so we are not going to do the same idea, not going to do the same methods of the Taylor series expansions because that will diverge. So what we do is that we divide the long time interval into a large number of short time intervals such that on each short time interval, we can essentially kind of apply the short time theory, and then we kind of iterate this to get to much longer times. Okay, so this is the first kind of key idea. The second key idea is to see this exact propagation of randomness. You see, there is a high non-trivial issue that you are starting from a time reversible system, which is either the Schrödinger or the collision particle system is time reversible, but you're trying to derive a time irreversible equation, which is either the Boltzmann or wave kinetic. They are all time irreversible. So there has to be a way to distinguish, going forward in time and going backward in time. And this turns out to require extremely precise information on this ensemble, on these, the set of correlations, let's say. And this is given in terms of these cumulative expansions. Okay, you think you have, in the Boltzmann case, let's say the S particle density is given by a sum of this factorized thing times this non-factorized thing in parentheses called the cumulant. And in fact, we'll need a very precise description in terms of explicit formulas, explicit kind of, we'll call the multi-layer molecule expansions of these cumulants. And we need to propagate that information kind of over time. Like if we have these whole expansions at this time, then we prove we have the whole expansion at the next time layer. So there are extremely complicated combinatorics involved that is given by expansions of these interaction history diagrams on the whole time interval. So these interaction history diagrams are called, we are calling them the molecules, which looks like this. So you see you have time 0, time tau. Tau is very small. Time 2 tau, you are going to very, very, high, very large time. And then in the Boltzmann picture, you see you are having these particles. So particles are given by their trajectory, kind of in colors. So for example, there's a red, and there is a blue, and so on. And then these nodes are collisions, the collision between particles. And then these molecule diagram, they're represented by these trajectories and the particles. And basically, and they're formed kind of in multiple layers. As you see, there are multiple layers divided by times. And then what happens here is that we have a particular formula for these cumulants. So cumulants, there's a spelling error. So the cumulants that is given by a huge integral associated with the molecule. So this integral, let me explain the integral on the left. So this is a product of delta n. Delta n are delta functions, Dirac functions that tells you, what happens exactly at this collision. There is a V1, V2, there is a V3, V4. What are the relations between V1, V2, V3, V4? Okay, and this is the initial data. The F is the initial data. So there are these particles coming from time 0, there are particles coming from time tau, time 2 tau, and so on, and these are the initial data, and you integrate in all the kind of velocity variables and the position variable and the time variables. So there's a huge kind of integral. Certainly I don't have time to talk about the details of this. On the right-hand side is a similar picture for in the wave turbulence setting, in the wave kinetic setting. And so the difference here is that each branching node corresponds to Duhamel iteration. So you have instead of a collision, you have a Duhamel iteration of different modes. And in the bottom, you're having these colored circles, which correspond to initial data. Remember, initial data are Gaussians. And by weak formula, these Gaussians are kind of going to be paired in order to give the correlation. And this is the formula right inside. So you see there is this time oscillator integrals, which in the end will turn into the same delta functions, but there is time oscillator integral, which makes things much more subtle in terms of cancellations. Okay, so we have these diagrams, and then the next thing is to analyze these diagrams. So there are two big components. One is analytic component, where we just to analyze these integrals also associated with diagrams. And the second thing is a combinatorial component, which turns out that the analysis of these integrals rely heavily on the combinatorial properties of the diagram itself, and this relies on a so-called cutting algorithm to isolate kind of the different features, the distinct features of these diagrams, and this allows us to complete the estimates of these integrals. So interestingly, this analytic component is much harder in the wave kinetic case. It relies on a lot of number theory and cancellations and precise oscillator integral estimates, but it's kind of a trivial, not completely trivial, but mostly much easier in the Boltzmann case because there is no cancellation needed. On the other hand, the combinatorial component is much easier for wave equation. You basically just do a naive greedy algorithm and that's it. But for the Boltzmann, it requires a very sophisticated combination of several different algorithms applied to several different settings, and you need to put them together in with a lot of cases to consider. Okay, so I think that's the only thing I could say regarding the proof. It's a long proof, and there's a lot of subtleties involved. Maybe to close it, let me mention a few kind of open problems. So this slide is concerning the wave turbulence setting. So first of all, the quantum Boltzmann equation. So again, this is completely open, and there are even kind of questions regarding on like what models you should take and what equation you should derive. You should derive the equation with quadratic cubic or just quadratic or just cubic. So it's kind of very much unclear at this time. And then regarding the wave equation itself, so you may have noticed I've omitted the hydrodynamic limit in the wave turbulence setting. That's because there's no hydrodynamic limit in the wave kinetic equation, because the limit behavior of wave kinetic equation is very different from that of Boltzmann equation. Instead of hydrodynamic limit, you're actually going to see a formation of either delta singularity in the wave kinetic equation, or kind of the so-called KZ spectrum in the different settings. And again, all these are open, like even going from wave kinetic equation to this behavior is open, because the going to this and like a much more. Sorry. And then there is this cross-linear equations and I don't have time to talk about. Maybe I mention a few in the. So the results by collaboration by Gallagher and Simonella. We can extend these to longer times. And the problem of single Boltzmann also may have single, and it's a question what happens to the particle system at this time. For example, if you want to go beyond this log, we're able to do. The case of Landau equation setting where you have many, but the collisions have much weaker. And then what happened concerning that. So, in summary, there is this thing. Although we were able to Hilbert's original program in these Boltzmann graphs, I would say this is from the end of the story. Is a story. I mean, probably the beginning. Thank you.
Yeah. Thanks for a very nice talk. So I wondered, there is also a hydrodynamic counterpart for the waves, as similar to the particle cases.
So there is hydrodynamic limit for the quantum Boltzmann equation, with the one with both quadratic and cubic. But for the wave equation with only cubic, I don't think there is such a thing.
Even for the inhomogeneous case?
No.
I see. Okay, thank you.
Any other question from here?
Just out of some curiosity, I'm not an expert, but in the particle case, like going from the discrete to continuum, do you have like kind of some energy functional which you can like use to go drive it to this? I mean, you get some energy functional in the limiter.
You mean the entropy or?
Yeah.
Yeah, so there is entropy certainly for Boltzmann. We somehow don't really see this entropy in our proof, so our irreversibility is caused by a different mechanism. But yes, it's interesting, like to see, like for example, what this in this monotonicial entropy would mean, like in terms of our proof. Like that's a question that we will probably look at maybe. Yeah.
And also for the kinetic thing, like can you drive it to some like what do you call this, like the limit equation?
You mean equilibrium for the wave equation?
No, not for the kinetic, the first part, the kinetic particle.
The Boltzmann equation, yes.
You had two parts, like the kinetic and
Yes, yes.
And you had a system, I think, like for the individual things, like. But can you get like maybe something like another picture, not the Eulerian, maybe the Lagrangian kind of picture?
Maybe. I mean, our work is concerned with derivation going to the kinetic equation. So, what would be the Lagrangian picture of that?
Oh, I mean, just like.
Yeah, but I don't know. I mean, we are not taking a Lagrangian picture in any case. Like we're having fixed coordinates. So, well, maybe we can do that post theory. Yeah.
Did you publish this in one place or in several places?
So there are several papers that are published in several places.
There you go.
So let us thank Professor Deng again.